Now let's talk about the acid-base properties of salts and discuss how to calculate the pH of a solution that contains a salt. In this first example, we'll think about the pH of a 0.1 molar sodium chloride solution. Now, the reason why we want to be thinking about the acid-base properties of salts is because a salt is a substance that produces ions in solution if it's soluble. And back in Chem 1A in Chapter 4, when we talked about salts, said that you could have a salt when you have a compound that is composed of a metal and a nonmetal, or you could also have a salt if you have a compound that contains a polyatomic ion. And if this salt is soluble in water, it breaks up into ions. Now, we know from having looked at the table of acids and bases over the past several lectures that many ions can act as acids or bases in aqueous solution. Therefore, putting a salt in water could affect the pH of the solution, and we need to think about how it might affect the pH. We'll first consider a solution of 0.1 molar sodium chloride. Sodium chloride is a soluble compound, and it is a salt because it contains a metal, sodium, and a nonmetal, chlorine. Now, because this is a soluble ionic compound, this will dissociate completely into its ions in solution. And it's helpful for us to write the dissociation reaction. So NaCl dissociates completely into Na plus ions in solution and Cl minus ions in solution. And this is a one-way reaction because the dissociation will be complete, 100%. It will not go back, and that's why we do not draw an arrow going in the backward direction. Now, for us to determine the pH of this solution, we'll need to list the major species that are present in the solution before any acid-base reactions occur. This is a strategy that we're going to use for finding the pH of all of these salt solutions, and we're going to use this strategy even more in Chapter 8 when we talk about buffers. In this strategy, the idea is to start out by writing what you have in the solution so that you can figure out what kind of chemical reactions might be possible. Those chemical reactions govern and control what the pH will be, so it's important to write the reactions, and really the best way to know how to write the reactions is to start with a list of major species. In this solution of sodium chloride, it broke up into Na plus and Cl minus, so those are major species in solution. And also in any aqueous solution, you will always have water as a major species, because for any aqueous solution, water is the solvent, so you're going to have a lot of water present in any aqueous solution. You should always include it as a major species for any aqueous solution. Now, having written the list of major species, the next step for us to do is to classify these species as being acids, bases, both, or neither, meaning that it would be a spectator. And the key for being able to do this is to take a look at the table of acids and bases and look for all of these substances. What we see is that the Cl minus ion is the conjugate base of the strong acid HCl. Conjugate bases of strong acids are ineffective as a base, and so that means that we'll say that the Cl minus is just a spectator. It does not act as really an effective base, and it doesn't act as an acid either. So this is a spectator. Furthermore, for water, we see that water appears both in the HA column as well as in the A minus column. I may have mentioned this before, but I will mention it here, and it's this. Water is going to be the weakest acid that we deal with in this class, and it's also going to be the weakest base that we deal with in this class. So when I put down water, I'll always list that as being a very weak acid or a base. Lastly, we have to think about the Na plus ion, and when it comes to the Na plus ion, or any metal cation for that matter, we will say that metal cations have no acid-base properties at all, at least not in the Bronsted-Lowry definition. And so the Na plus ion will just behave as a spectator. That will hold true for any metal cation. Again, we will say that they will never have any acid-base properties, at least not in the Bronsted-Lowry definition. All right, so just to kind of summarize where we are here again, right? Metal cations, no acid-base properties, so they'll always act as spectators. Anions or conjugate bases from strong acids are ineffective bases, and so those are also spectators. So what we have here is two spectators and water. Therefore, essentially, in terms of acid-base chemistry, all we have controlling the pH is just water. And so this is going to end up being a neutral solution, right? Like water has a pH of 7. Na plus doesn't change the pH. Cl minus doesn't change the pH. And so this solution will have a pH of 7. It will be completely neutral. There are many salts that do make neutral solutions. And in order to have a salt that makes a neutral solution, you must contain both of the following: a metal cation, right, like Na plus, K plus, Ba2 plus, any metal cation, because that has no acid-base properties. And in addition to this, you must also have the conjugate base of a strong acid. So like the chloride ion, the bromide ion, the nitrate ion, these are all conjugate bases of strong acids, and so these are ineffective bases. These are also spectators. And if you have a salt that contains both of these things, then both the cation and the anion will have no effect on the pH, and you'll end up with a neutral solution. Some more examples might be compounds like potassium chloride, potassium nitrate, sodium bromide, sodium nitrate. All of these would make neutral solutions because in every case you have a metal cation paired with the conjugate base of a strong acid. That brings us to the end of this example. In the next video, we're going to take a look at calculating the pH of a 0.1 molar NH4Cl solution.